Welcome to The Explainer. You know, the unseen mechanics of shallow foundations literally dictate the survival of every single structure we build. Today, we're jumping right in and dissecting the hidden engineering that fights gravity and keeps our built world upright. Let's get started.
There's an old absolute truth in structural engineering. The most important part of a building is the part you never see. It's true. Before we ever build up, we've got to dig down. If the superficial soil strata actually possess sufficient bearing capacity to support the immense loads of a structure, well, we utilize shallow foundations. But as you might guess, that requires some incredibly precise diagnostic science.
Because here's the ultimate threat to any structure. It isn't just settling, it's the absolutely catastrophic effect of differential settlement. When one corner of a building drops further than the rest, it generates these immense shear stresses. It literally bends and tears the structural frame apart, usually beyond repair.
So, it really comes down to uniform versus differential settlement. A uniform, totally even sinking of the entire structure is usually fine. It's of little consequence and practically expected in many cases. Differential, or uneven sinking, on the other hand, that is the primary enemy our foundation designs exist to neutralize.
Okay, here's our blueprint for this explainer. First, the battle against settlement. Next, the rules of foundation design, followed by basic shallow footings. Then we're going to look at solving property line problems. And finally, raft and mat foundations.
Rules of foundation design, the diagnostic process.
Engineers don't just guess out there. Their process is strictly chronological. Step 1. Prepare a base plan showing all columns, load-bearing walls, and estimated loads. Step 2. Study the allowable bearing pressures of the soil based on detailed geotechnical reports. Step 3. Determine the depth of the foundation. According to structural codes, footings generally have to extend at least 0.5 meters below the natural ground level. That's just to ensure they reach a suitable, weather-resistant bearing. And finally, Step 4. Compute the precise dimensions based on all those combined loads and soil pressures.
Now, allowable bearing pressure. What is that? Well, it's the absolute maximum pressure a footing can safely exert on the supporting soil without exceeding those settlement limits we talked about earlier. Think of it like the maximum weight you can put on a trampoline before it bottoms out and touches the ground. If you exceed this allowable pressure, the soil matrix compresses way beyond its elastic limit, and boom, your structure starts sinking unevenly.
Section 2. The basic players. Standard shallow footings.
Let's do a quick roadmap of our shallow footing toolkit. We've got the isolated footing, the strip footing, the combined footing, the strap or cantilever footing, and the raft or mat foundation.
First up is the isolated footing. Honestly, this is the simplest and most economical choice. It's designed to support a single column. Basically, it acts like a giant snowshoe, a load-distributing pad just for that one column. By providing a wide concrete base, it significantly reduces the bending moments and shearing forces that would otherwise punch right into the dirt.
Next is the strip footing, which you might also hear called a continuous footing. It does exactly what it sounds like. It runs continuously under load-bearing walls or closely spaced columns, spreading structural pressure over a much larger, linear area. If you've ever walked by a construction site for a low-rise masonry building and seen those long trench foundations being poured, well, you've seen strip footings in action.
Section 3. Engineering curveballs, the property line problem.
So what happens when things don't go according to plan? Imagine you have to build right up against a property line, or maybe an immovable utility line, and you absolutely cannot center your column on the footing. If your column sits on the very edge of the concrete pad, it creates a massive, eccentric load. This generates a huge overturning moment at the base. Essentially, this uneven weight distribution genuinely threatens to tip the entire building over. It's an engineer's worst nightmare.
But there's a brilliant solution for this, the strap or cantilever footing. To stop that off-center edge column from overturning, engineers connect it to a completely stable interior column using a massive, rigid tie beam. We call that the strap. It perfectly balances the asymmetrical load, kind of like a seesaw. The heavier, stable interior column acts as the counterweight, firmly anchoring that eccentric exterior column in place.
Now, the engineering mechanics behind this strap beam dictate that it has to follow some pretty strict rules. It connects two isolated footings, it's assumed to be infinitely rigid, and it acts purely as a flexural member. What does that mean in practice? Well, it means the strap actually floats slightly above the soil, or the soil beneath it is intentionally loosened. Its only job is to transfer that unbalanced shear and moment over to the stable interior footing. It absolutely does not transfer load directly into the dirt beneath it. No way.
Another really elegant solution for tight spaces is the combined footing. When individual isolated footings would overlap because columns are just spaced too closely together, engineers unite them into one large pad. The critical trick here is ensuring uniform soil pressure. They do this by carefully designing the dimensions so that the center of gravity of the combined column loads perfectly matches the center of gravity of the footing area itself. Pretty clever, right?
Section 4. The last resort. Raft and mat foundations.
When all else fails, we turn to the raft or mat foundation. This is a massive reinforced concrete slab that covers the entire footprint of the building, supporting multiple columns and load-bearing walls. Engineers deploy this heavy-duty, ultimate solution when the soil-bearing capacity is just incredibly low, or when calculating individual footings reveals they take up more than 50% of the building's base area anyway. It acts as one continuous structural pad for the entire structure. It's like one giant snowshoe for the whole building, uniformly distributing massive weight to aggressively reduce any chance of differential settlement.
So, we've covered the hidden engineering toolkit that keeps our world structurally sound, from those basic isolated pads all the way up to massive underground rafts. Next time you walk down the street, I want you to look around and ask yourself, what hidden concrete shapes are actively fighting gravity beneath your feet right now? Because it's true what they say. The most important part of the city truly is the part you never see. Thanks for joining me on this explainer.